Hey guys, Dr. J here, and in this video we're going to start talking about weather and weather services, and particularly those topics that are relevant for the Part 107 knowledge exam. You can get more information about weather and weather services from the PHAC Chapter 12 or from the Remote Pilot SUAS Study Guide Chapter 3 Part B. Now there's two parts or two components to weather, two aspects that we need to learn about when we're getting ready for the Part 107 exam. One is going to be some actual knowledge, information about the weather, how it works, and how it impacts aircraft. The second part of information is going to be where to get the information, and that's going to be coming from weather reports that are called METARs, and these METARs are just weather reports, nothing else, but they're a little bit complicated and difficult to read, and they're kind of like a coded message in some ways. So we're going to learn how to read those, and we're going to learn about the weather. Now, weather is actually one of my favorite topics. I almost wanted to be a meteorologist when I was a young person and didn't end up going that route, but still am really fascinated by the weather and all the different things that are involved with it. And there are a number of aspects of the weather that are really important for pilots in general and UAV pilots in particular, so we're going to talk about those. And the first aspects that we're going to talk about are three fundamental factors: pressure, temperature, and water vapor. And understanding just in general how these work in the atmosphere, it's going to help you sort of think through when you're going to do a flight, are the weather conditions appropriate for making this flight that I want to do? Now let's go back to the very basics to start with. Talk about the composition of the atmosphere is about 80% nitrogen, 20% oxygen, and a few, probably even less than 1% trace gases, including carbon dioxide. And the atmosphere is organized into we organize it into layers, and the most important layer for us in terms of thinking about what's going to affect our flying is the troposphere. And the troposphere is the lower 5 miles, maybe 5 to 10 miles really, of the Earth's atmosphere. As you get up above 10 miles or so, then the atmosphere becomes much, much thinner and behaves in some interesting ways and weird ways, and really is not going to be super relevant for UAV flying. The part that we're going to focus on is that lower 5 to 10 miles of atmosphere called the troposphere. And most weather occurs in the troposphere. So storms and storm systems and wind and all those kinds of things are going to be in the troposphere, that lowermost layer. Now, in the troposphere, temperature decreases, and this is something you need to memorize. Temperature decreases about 2 degrees Celsius per 1,000 feet. What does that mean? As you go up in the air, 1,000 feet, the temperature is going to drop about 2 degrees Celsius no matter where you are. So if your ground temperature is, let's say, 10 degrees Celsius, and you go up 1,000 feet to 1,000 feet above mean sea level, the temperature at 1,000 feet above mean sea level, where the temperature is 10 degrees Celsius, will be 8 degrees Celsius. You go up another 1,000 feet, it's going to go down to 6 degrees Celsius, and so on. So if you're at 10 degrees Celsius at sea level, and you go up 5,000 feet, you'll be at freezing, 0 degrees Celsius. Now, this is I will say, as a scientist who does a little bit of atmospheric studies, this is a gross simplification, but in general, for us as UAV pilots, this is going to be a good enough approximation of how the atmosphere works that it'll work for what we need to do. Now, temperature is actually really important for driving weather on the Earth. Warm air rising, cool air sinking, and this is the general principle that's going to be the case for everything that we're going to talk about. Warm air is going to be less dense, and less dense air is going to rise. Cool air is going to tend to be more dense. It's going to densify as it cools, and that's going to tend to sink. And this rising and sinking pattern is what does all sorts of things. It sets up our global weather circulation patterns. So globally, air is warmed at the equator especially and rises, and that sets up these different circulation patterns. Basically, it's just air that's getting warm and rising, and then gets cool, cools back down, and then falls back down to Earth. And that sets up these global weather or global air currents, which end up being our prevailing winds all over the globe. So we have rising and falling air as it warms and cools at a global scale. We also have it at a very local scale. You may have seen hang gliders, and hang gliders use rising air currents at a very small scale. Same principle. All right, so let's talk more about pressure, temperature, and humidity. And let me just say right at the get-go how these affect drone performance. Pressure, temperature, pressure P, temperature T, and I use the letter E to just refer to humidity in general. Now, how do these affect drone performance? One way is, well, you can see all the different ways. And the basic way is that if you have more air, propellers work by pushing against the air. And so if you have less air molecules to push against, lower density air, you're going to have a more inefficient drone performance. So takeoff and landing will be affected, actually for both fixed wings and quadcopters. Rate of climb, flight ceiling, how high you can fly, your payload weight, how much weight you can carry and for how long, how fast you're able to go, and how maneuverable you are. All these things are going to be affected by your pressure, temperature, and water vapor conditions. And the reason is, overall, is it's the changing density of the air. So lower density air is going to be less performant. Higher density air, there's more air molecules for those propellers to push against or for the wings to push against. And so you'll be more efficient overall with a higher density air. And so what are the factors, the pressure, temperature, and humidity factors that contribute to lower and higher density air? Atmospheric pressure is measured in several different ways. One is atmospheres. So 1 atmosphere is the standard amount of pressure that the Earth's atmosphere has at sea level on what's called a standard day. Pounds per square inch, PSI, that's a common one in the United States. Inches of mercury is another one that's been common, especially in the past, and is still used in aviation and will be very important for us. And then hectopascals is just another unit using SI units for measuring atmospheric pressure. So these are the conversions between these. 1 atmosphere is 14.7 psi, 29.92 inches of mercury, or 1,013.2 hectopascals. And in particular, the number that you're going to want to remember for the Part 107 exam is that 1 atmosphere is equal to 29.92 inches of mercury. Standard atmospheric pressure at sea level is, as I said, 1 atmosphere and 29.92 inches of mercury. And as we change our elevation, the pressure is going to change in a very similar way to what we said about the temperature. So again, this is as someone who thinks a lot about the atmosphere and the troposphere, this is a gross simplification, but it works for us. And so what we're going to say is that pressure decreases at a rate of about 1 inch of mercury per 1,000 feet of elevation gain. This is another one of those numbers that you're going to want to memorize. So temperature decreases 2 degrees Celsius per 1,000 feet. Pressure decreases about 1 inch of mercury per 1,000 feet of elevation gain. So as you go up 1,000 feet, you lose 1 inch of pressure, even if at sea level your pressure is exactly equal to 1 atmosphere. All right, so one quick definition before we move on is the definition of a standard day. And this is what I've already mentioned. Here's our 29.92 inches of mercury at sea level. And then the standard temperature that goes along with that is 15 degrees Celsius. So 15 degrees Celsius, 29.92 inches of mercury at sea level is a standard day. And a standard day is going to be what everything else gets referenced to. So if we're going up in elevation, so if we have weather systems come through where the pressure is changing, if we have temperature changes, we're going to be comparing everything to this standard day. And the conditions for flying your UAV, let's say we get warmer than the standard day, that's going to reduce the air density compared to a standard day, and that's going to reduce your flying ability in the same way. Lower density air is going to be more difficult to fly in because, as we said, those propellers are pushing against air molecules, and so if there's less air molecules to push against, then it's going to be more challenging for that drone to maneuver and fly and carry payloads and things like that. Another definition is pressure altitude. So for pressure altitude, this is the altitude correcting for pressure changes. This is the altitude that's felt by the drone, and this is a little bit a weird way to say it, to call it this, but basically the pressure altitude is the altitude that you would be at if you were in a standard day. So basically what's going to happen is if the pressure changes, and it's going to turn out actually temperature is the same way, if the pressure or temperature change from standard conditions, the effective altitude that your drone feels is going to be different from its actual altitude. This is just a way of compensating for changes in pressure and temperature which affect the performance of your drone and making it all kind of a standard. So basically we convert pressure and temperature changes to an altitude change. And that's going to be our pressure altitude if we're just accounting for pressure. And if we account for pressure and temperature together, that will be our density altitude. So let's look at a figure just to illustrate all of this. So I've got here our standard day conditions. So here at 0 feet MSL, we're at 29.92 inches of mercury. And as we go up in elevation, we're going to decrease our pressure systematically, 1 inch mercury per 1,000 feet. So 28.92 at 1,000 feet, 25.92 at 4,000 feet, and so on. And here we are flying our drone. Now what's going to happen is, of course, the drone performance is going to be reduced at higher altitudes. So that should be obvious. Our pressure is lower, our air density is lower at higher altitudes, and so the drone performance is not going to be as good flying up here at, let's say, 4,500 feet as it is going to be flying at sea level. Now, what happens if we reduce the pressure at sea level? So here now at sea level, we're at 28.92 inches of mercury. This might be because of a low pressure day from a low pressure weather system coming in. And so now at sea level, we're no longer at a standard day conditions. We're at 28.92 inches of mercury at sea level. And so what that basically does is it changes the effective elevation that your drone is flying at. And so now, instead of flying at 4,500 feet MSL, we're flying at something which is the same pressure. We're flying at a pressure which is, let's say, almost 23.92. That's going to be almost 6,000 feet MSL. So in this case, I've decreased the pressure by 1 inch of mercury, and so I've increased the effective elevation of my drone by 1,000 feet. You guys see how that works? By decreasing the pressure, the overall pressure, this whole column of pressure values goes down. We're still changing by 1 inch mercury per 1,000 feet. It's just the overall pressure that has decreased. And so that increases the altitude. The pressure that I'm feeling right now in this low pressure day is going to be equivalent to what I would have felt flying at almost 6,000 feet MSL. So my effective altitude, my effective elevation that I'm flying at goes up on a low pressure day. So let's do a quick example. The barometric pressure reported for Rolla, Missouri on March 14th, 2023 was 30.04 inches of mercury. Now, Rolla is 1,122 feet MSL, and of course, you remember 29.92 inches is standard pressure at sea level. But we're not at sea level, we're at 1,122 feet. So what we're going to do is we're going to take our elevation correction, we're 1,122 feet divided by 1,000, and we're going to multiply that by 1 inch of mercury. So every 1,000 feet is 1 inch. And then we're going to subtract that out from our actual measured barometric pressure at on the ground at Rolla at 1,122 feet. So this is our conversion to inches of mercury correction. That number, whatever that is, it'll be a little bit, it'll be 1.122 inches of mercury. We're going to subtract that out from 30.04 inches of mercury to get our sea level condition. So this now, 28.918, that's our barometric pressure at sea level based on the pressure at Rolla. Pressure at 0 MSL, 28.918, is 1.002 inches of mercury lower than standard. So this is similar to the example that we just looked at. We're an inch of mercury below standard pressure conditions. So our pressure altitude is now going to be our actual elevation, 1,122 feet, plus the scaled change in pressure. So we had 1.002 inches of mercury lower. So we're 1,000 feet times 1.002 inches higher than the actual elevation in Rolla. And so we need to add that to our actual elevation. That's 2124. If the pressure was 1 inch higher than standard conditions, then we would subtract. We would subtract the altitude here away from our actual altitude. If we were, say, 1 inch higher pressure than standard pressure conditions, then we would be at just about at sea level. But since we're an inch lower, we're actually double our elevation, about 2,100 feet MSL, because of the low pressure conditions. So our pressure altitude has gone from 1,000 feet above sea level to 2,000 feet above sea level. So let me back up here just for a second, just to review. We've got our standard pressure conditions, 29.92 inches of mercury at sea level. We're decreasing pressure at 1 inch mercury per 1,000 feet as we go up in the air. Again, it's a simplification, but that's what we're using. And then as the pressure changes, that's equivalently going to affect the pressure at all the different elevations above us. And so our effective flying height, no matter what our actual elevation is, will also be affected. And it will be affected as if we were flying at a different elevation than what we actually are. If the pressure goes down, it'll be effectively a higher elevation. If the pressure goes up, it'll be effectively a lower elevation. All right, now there's one more complexity in this, which is that when you're looking at the weather reports, we mentioned the weather reports before, those are for a particular airport. Those are going to be reported using the equivalent pressure at sea level. So they're going to do the conversion for you of converting the pressure at the airport to the pressure at sea level, the equivalent pressure at sea level for that airport, for the given pressure conditions. We'll be able to take the difference between that pressure and just 29.92, meaning the pressure that's reported at that particular airport. We'll subtract that out from 29.92, multiply by 1,000, and that's going to be our pressure altitude, plus the airport elevation. So as an example, if we have an airport at 5,000 feet above mean sea level, and the reported pressure from the weather report for that airport is 29.79 inches of mercury, that's going to be 29.92 minus 29.79. That's a difference of 0.13. We'll multiply that by 1,000. That's 130. And so the actual airport pressure altitude, the pressure altitude of that airport will be 5,130 feet. So at the airport, it'll have a pressure altitude of 5,130 feet. Now you might say, why do they do this? Why do they report the pressure as if it's at sea level when it's not? Pilots use the pressure at sea level to calibrate their altimeter so that they know how high they're flying. And so as weather systems come and go, airplane altimeters are using barometric pressure. They're using this fact that the pressure goes down 1 inch per 1,000 feet to tell their elevation. And so if there's weather systems moving through and their altimeters are wrong, then that obviously would be a big problem. And so that's why these weather reports report the pressure as if it's at sea level. So then the pilot can just calibrate their altimeter to use that sea level pressure and then get their correct altitude. Okay, so we've talked about pressure quite a lot. We'll talk about that more as we talk about storm systems and wind and things like that. But let's quickly talk about temperature. Temperature is going to be incorporated into something which is like pressure altitude, but that is called density altitude. So density altitude actually takes into account both temperature and pressure. It's the altitude that the drone feels when it's flying. We already talked about that. You can be flying at 3,000 feet, but feel like it's 5,000 feet. It's exactly the same issue as the pressure altitude. The only difference now is that we're going to incorporate temperature. And what do we have here? So here's our pressure altitude calculated using that formula we saw before. And then LT is going to be our local temperature. ST is going to be the standard temperature, again, corrected for our elevation. So we need to make sure we do that. And then there's this 120 factor. And that 120 factor is a conversion factor which goes from temperature difference to equivalent elevation. So let's do an example. Temperature is 3 degrees Celsius. Our standard temperature, this is going to be going back to Rolla. Standard temperature at 1,122 feet is going to be what? It's going to be 15 degrees. That's our standard temperature at sea level, minus 2 degrees per 1,000 feet. That's our decrease with elevation, multiplied by our elevation. So this is 1,122 feet. We take that and we multiply by this conversion. So 2 times 1,122 divided by 1,000. This is just a conversion factor. That's going to be 2.24 degrees. So we take 15 minus this whole thing, 2.24, and we get 12.8 degrees Celsius. Now, I know this is a little bit of math, so if you're not used to math, make sure you kind of go through here. I would write this out. I added the units in here, so you see now the units 15 degrees C minus this conversion, 2 degrees C per 1,000 feet, multiplied by our 1,122 feet elevation in Rolla. This all gets multiplied out first, then you do the subtraction. 15 minus whatever this works out to be, which in this case is 2.24 degrees. That gives us our 12.8 degrees C. So standard temperature at 1,122 feet is 12.8 degrees C, but our actual temperature was 3 degrees C. And so now we do this conversion, our local temperature minus our standard temperature. So we do local temperature, 12.8, minus our local temperature is 3, local temperature, 3 degrees, minus our standard temperature, 12.8 degrees C. That's negative 9.8. We're going to multiply that by 120 and add to our pressure altitude. So in the example that we just did before, our pressure altitude was 2124 feet. Now we're going to work out this math. 3 minus 12.8, that's going to be negative 9 something, times 120. That gives us negative 1176. We have a negative 1176, plus our pressure altitude, 2124. Our final altitude, our density altitude now, which takes into account both pressure and temperature, is going to be 938 MSL. So you notice because our temperature is colder, even though the air pressure is lower, which causes the density altitude increase, the temperature being lower causes the density altitude to decrease. So we're colder than standard conditions, and we're lower pressure than standard conditions, and those two things work out so that our actual density altitude is actually about the same, roughly 1,000 feet MSL, as our actual altitude. So in this particular case, the temperature and pressure kind of cancel each other out a little bit. This will not always be the case, and especially once you figure humidity into the mix, then things get a little bit complicated, but we'll talk about that in a second. So as I've mentioned, you can't just look at the actual altitude where you're going to be. You need to look at the density altitude, which can be calculated based on the pressure and temperature. And then high density altitude means low drone performance. You're effectively flying at a higher altitude than you actually are. Low density altitude means better drone performance. You're flying at a lower altitude, closer to mean sea level, closer to standard conditions. You're going to get better performance. Low T, low temperature, high pressure. That's going to be equivalent to low density altitude, high temperature, low pressure. That's going to be lower density air. And so that's going to give you a high density altitude. Your high density altitude corresponds to a low density air, and a low density altitude corresponds to a high density air. So I know I'm going back and forth here a lot. This is a bit of a confusing topic because some things are opposite of each other, right? So less dense, just use the idea of density. More dense air is going to be at lower altitude, and that's going to be colder. It's going to be higher pressure. Those things all go together. Less dense air is going to be lower pressure, higher temperatures, higher elevations, higher density altitudes. The last factor is humidity, and I won't say too much about humidity other than to say high humidity is going to negatively impact drone performance. The humidity acts as like it lowers the density of air. The more humid it is, the lower the density of the air will be. And what often happens is you have hot and humid weather at the same time, and so that's going to be really problematic for drone performance.